Now it's time to look at the energy of a reaction again. We looked at this back in the thermodynamics unit. This would be a reaction where the energy of the reactants is right here, energy of the products is right there, and then there's this little hump that they have to get over in order to go from reactants to products, and this little hump is called the activation energy. So if you think of something like methane, that's what we use to light our Bunsen burners. If you just mix methane with oxygen in the air, nothing happens, no reaction. In order to get a reaction started, what do you have to do? You've got to give it a little spark, a little match light, and that match light provides energy for it to get over this hump and generate your products. And so that's what triggers the reaction, and that's what activation energy is. And we symbolize activation energy with E subscript A, so energy of activation. And this right here, the change in E, that would be the change from the reactants to the products. That would be the delta H stuff that we talked about. So in this case, we've got more energy there than there, so this would be an exothermic reaction. But that's neither here nor there. Right now, we're more concerned with the idea of the collision. So in order for reactants to form into products, it's not just about the fact that they touch each other. It's not about the fact that they touch with the proper orientation. They also have to touch with the right amount of energy. Okay, so the energy from the collision has to be greater than the activation energy, because if A, B, and C collide, but they don't collide with enough energy to get over that hump, no product's going to form. So the collision energy has to be enough to where it would overcome this energy right there and make it over to the other side. And energy from collisions would be kinetic energy, which is the energy of motion. This is another reason why heating up a reaction speeds it up. More energy, more motion. If we got more motion, we've got more power for them to collide and overcome that activation energy. So if you have a collision that does not have as much energy as it needs to get over the hill, that would be like if you have a little cart down at the bottom of a hill and you give it a little push. The cart's going to go up partway up the hill, but then it's just going to come back down. And so that's what happens with collisions that have lower energy than what they need to get over that activation energy hump. And so this is what's going on when you turn on a Bunsen burner just in a room without giving it a spark. That methane, that oxygen, sure they're colliding, sure they're mixing, but they're just kind of going up that hill, but then they don't have enough energy to form the actual products. So here's another Maxwell-Boltzmann distribution that shows the average kinetic energy of molecules at certain temperatures. So if you've got a particular set of reactants at 500 Kelvin, the average, or the molecules, are going to fall within this range of kinetic energy. And if they're at 1,000 degrees Kelvin, 1,000 Kelvin, they're going to fall in this range of energy. And so right here would be the line that marks the activation energy, so the kinetic energy needed to overcome that hump. And you see as we heat up the temperature, you have more reactants in this green zone that fall into that over the activation energy range than you would at a lower temperature. So a unimolecular reaction is a reaction that involves just one molecule. And so an example of that would be like ozone. So O3 decomposes into oxygen and an oxygen radical. And so just that reaction written out normally would be O3 breaks into O2 plus O. And so this is a pretty common decomposition reaction that actually happens up in the ozone layer. So the question is, if we think of the energy diagram for this guy, so we've got our reactants right there, activation energy, and our products right there. So in order for them to get over that hump right there, they have to collide with the proper amount of energy. But if O3 is just breaking apart into O2 and oxygen, where's the collision happening? There's nothing for it to collide to because it's a unimolecular reaction. And so actually, in the background, there's always some kind of solvent or other particle in there that triggers these reactions. And so in the case of O3, it'd be mixed with M. M could be a solvent, it could be a catalyst, whatever it is. But O3 actually collides with that solvent, and that's what causes it to break apart into O2 and oxygen. And then left in the end again is still that M. That's why we don't actually write it into the reaction, because it's not chemically changing, therefore it's not part of the reaction. So in a decomposition reaction then, there actually is collisions going on. It's collisions between the molecule and then some kind of background element that we don't really write into the equation, we don't really think about. And likewise, in order for that decomposition to occur, you're going to need that proper activation energy, so it has to hit that background molecule with enough energy. And activation energy does play a big role in reaction rates as well. So rates, or reactions that happen very, very quickly, typically have a lower activation energy. That means they don't need much kinetic energy in order to overcome that hump. If they don't need that much kinetic energy, they can happen a lot faster. As opposed to reactions that have a high activation energy are going to take a lot more energy put in, and therefore they can't occur as easily. So something like this, room temperature might provide enough energy. Something like this, it might require very, very hot surface or hot area in order to get enough kinetic energy to get over that hump. So if we think of something like iron rusting, if you leave a piece of metal outside, it takes a very, very long time for that piece of metal to completely rust. That's because it's got a higher activation energy, and so the reaction as a result moves very, very slowly. As opposed to something like sodium and water. When we drop sodium in water, it reacts fairly quickly, and that's because it has a much, much lower activation energy. The energy in the room, the kinetic energy of the room, is enough to drive that reaction over to form our products. So in the previous video, we talked about reaction rates. In summary, though, knowing what we know now, there's really three conditions that must be met in order for reaction to occur. There must be a collision, first off. They have to get to each other, they have to hit each other. They also have to hit each other with the right orientation that could yield the reaction, and the energy of the collision has to be greater than the activation energy. Now, of course, where would we be without talking about forward and reverse reactions, such as an equilibrium? So the activation energy for a forward reaction is not the same as the activation energy for a reverse reaction. So just looking at two general reactions, one being the reverse of the other. For the forward reaction, here's our reactants, there's our products down there. So in order to get from reactants to products, they have to overcome that hump right there. And so they're just going from this height up to that height to get over here. If we reverse this reaction, though, and we've got our products now on the reactant side, now they have to go from this height up to that height. And so the activation energy for this reaction is actually higher than it is for this reaction, because they need more energy to get from products up over that hump and then to reactants. Now, it just wouldn't be fair if I finished this video without giving you guys an equation. And the equation of this video is the Arrhenius equation. And so this one involves the rate constant, so we say our lowercase k there. This is the same k that we use in the rate law. And so we can use the rate law to get that k value, or we can use the Arrhenius equation to get the k value for the rate law. So it's the rate constant for a particular temperature. And then we have A, so A is a constant related to the frequency of collisions and the probability the orientation could produce a reaction. So depending upon the shape of a molecule, maybe sometimes the proper collisions are easier than they are for other molecules, and so that's a constant for a particular reaction. It does not change with temperature though. And then it's to the E, and so this would be the anti-natural log, raised to the negative EA, so that's the activation energy, which is in joules, times R, and for our R value we're going to use the 8.314 version because it's got joules in it to match with the EA, multiplied by temperature, which has to be in Kelvin, to go with our R. And then wave our hands, work a little magic, and we can rearrange the Arrhenius equation to give us this setup right here. And what this setup is another y equals mx plus b. And so if we graphed the natural log of k, the rate constant, for different temperatures, and so we would do the natural log of different k's and different temperatures inversed, we would get a slope that is equal to essentially the activation energy. And so we could calculate the slope because it's activation energy divided by R. R is always 8.314. And so we can use that to find the activation energy of a particular reaction. In order to find this, though, we'd have to do the reaction at different temperatures. Different temperatures would yield different Ks. And so that's going to tell us how much the activation energy plays a role in the process of this reaction. So we determine the rate law by doing a reaction at different concentrations. We determine the activation energy by doing a reaction at different temperatures. So here's an example of what we would see. For a natural log of k versus the inverse of time, we'd get a nice straight line like this. And so in order to find the activation energy, we would use the slope of this line to find it. And so rise over run looks like we're going from -5 to -1. And then for our run, we're going to 3.8 from 3.4. And so if we just do our rise over run equation, we're going to get a slope that is equal to -1.0 times 10 to the 4th. And the units on that, since we are dealing with Kelvin on the bottom, looks like it's going to be Kelvin. And so looking at that rearranged Arrhenius equation again, what we found was the slope, and the slope is going to be that guy right there. And so that means negative E of A over R is equal to -1.0 times 10 to the 4th K. Now, R is 8.314, and so we'll be able to just swap that guy out for 8.314 joules per mole Kelvin. And then we can rearrange this equation to solve for EA, which is the activation energy, by multiplying both sides by that R value. And when we do that, it's going to cancel out the K's because we have K on top and bottom. And what we will get as a result is approximately 83,000 joules per mole. So that means in order for this reaction to occur, each mole of reactant is going to need 83,000 joules of energy to get over that activation energy hump.